We're going to look at an application of the impact calculations that we did earlier. We're going to look at a toy that's called a Newton's Cradle. You've probably seen it, a desktop toy that consists of some solid steel spheres and usually suspended by wires, allowed to strike each other. And because these are solid steel and relatively small in size, they tend to have a coefficient of restitution that's very close to 1. Now we know that that's not going to be exact value of 1, that there's no such thing as a perfectly elastic collision, but these are close enough that the response is very close to being that coefficient of restitution of 1, and that assumption will allow us to predict what's going to happen here and to simulate that. So let's go back and look at a simulation that we did earlier. We have two masses, in this case equal masses. We've set the coefficient of restitution equal to 1. The one on the right is going to be at rest and struck by the one on the left. And we see what happens. All of the energy is transferred to the one that was originally at rest, and the one that was originally in motion then comes to a stop. So we can kind of expand that by looking at what happens if we have more than two coming together. So we have these three that are at rest struck by the fourth, and again with a coefficient of restitution of 1 between all of these, then we see what happens here is that it really, you can think of this as being a series of collisions between the first and second and third, etc. And at the end, then the last one goes off at the same velocity that the first one came in, and the other three are now at rest. So based on that, we would predict what happens in the Newton's Cradle here is that when we release the first ball, that there's going to be again a series of collisions, and the last ball will end up coming up to the same height at which the first ball was dropped. And we can see that that's pretty much what happens. We do start getting a little bit of motion in the ones in the middle, and when you actually run this, do the real thing, you'll actually see that does happen. Again, not perfectly elastic collisions, and so these balls don't remain perfectly still during the whole time, but pretty close. So the question might be now, what happens if instead of dropping 1 from a height, what if we pull back 2 and drop them? Well, again, we can kind of look at that on our linear model here. Going back to this configuration, again, there's only 4 instead of 5, but we'll get the same idea. So if these two on the left are coming in at the same speed and strike the two on the right, then again the initial ones will stop, and the two on the right will take off. So if we kind of try to think of what that means for our Newton's Cradle, then what we would predict would be when we drop these two that will make the contact, and that the two on the left will then fly out, and the one in the middle essentially will stay motionless. And we can see that again is the simulation. And if we do it for dropping 3 balls, it's similar kind of thing. So in this case, the one in the middle stays in motion the whole time during this sequence of collisions. So one more thing we might ask ourselves is, what would happen if instead of the balls all being the same mass, what if we make one that is twice the mass? And I don't know if that's the exact ratio here, but the one on the right I've made approximately twice as heavy as the other balls. So there's a couple of possibilities that you might think of. One is this ball will come down and strike these, and because it has twice the mass, therefore twice the momentum, that the 2 balls on the end will go flying upwards. The other possibility we can think of is that maybe when this one comes down, that we'll get this chain reaction of collisions, and so the one on the left will fly out by itself but up to twice the height that the initial ball is dropped from. So both of those seem like they could be logical, but let's go back again to our linear model here. And so here's again one mass that's twice as heavy as the other, coefficient of restitution equals 1. And if we see what happens, again we've done these calculations already, but you can see after the collision, the heavy one is going to keep moving. And so we might predict that what's going to happen in this modified Newton's cradle will be just that after this heavy ball makes the initial contact, it's going to keep moving and generate again another series of contacts there. So we'll play this in pretty slow motion here. And so you can see that, well, the last one does end up flying up quite a bit higher, but there are all these intermediate contacts as well. If you simulate that out further, you'll see that the pattern gets a little bit more disorganized the further that you take this out. So again, this Newton's cradle is a simple looking little apparatus, but if you really try to study what's going on within here, you really can open a lot of cans of worms as far as the calculations and what the times are, whether you need to have a little bit of space in there or whether it works when they're initially in contact. You can also search for there's a video that's on YouTube from Mythbusters where they try to make a giant one out of very large spheres. But because of the fact that the spheres weren't solid, they had to fill them with concrete, then their coefficient of restitution was much less than 1. But again, it's kind of a fun one to watch.